An installation's mission depends on its built infrastructure. That infrastructure in turn depends on civil engineers performing their mission to achieve maximum lifecycle performance of every asset. Our customers rely on us, and the ops flight relies on you to achieve optimal maintenance decision making. Let's begin with a review of our maintenance history. From there, we'll take a look at maintenance cost elements. Then it's off to the lifecycle ownership and investment planning. Next, we'll discuss work scheduling and understanding how we can strategically develop maintenance programs. We will conclude by discussing how we hold requirements for optimization. There's no hiding that CE does a lot of maintenance. Thanks to NextGen IT, we can readily discover where we log our hours. This table shows the percentage of logged direct time by work task priority. The good news is we're spending less than 2% of our total direct time on emergencies. Additionally, we're only spending slightly over 2% of our time doing enhancement work, priority 4s. Preventive maintenance is only taking about 20% of our time, and another 10% spent, at least at the enterprise level, doing plant operations. I'll do the math for you on corrective maintenance. We're logging just about 2/3 of our time to priority 3 work. Before we can continue, you must have a foundational understanding of CE maintenance costs. This section will discuss the cost elements on a work task, why tracking cost is important, a brief overview of CE shop rates, understanding material cost, and finally reimbursements. Every work task can capture up to 3 types of core work activity cost type. The most common, of course, is going to be labor logged in hours. Most work is going to require material, and NextGen IT is set up to capture material cost regardless of the methodology used to procure those materials. Some work activity may require the assistance of a third party, and in this case we capture the service cost for that contracted support. Now let's take a look at how work task costs interact with other aspects of CE business. Every work task's cost is associated to the real property asset for which the work was performed. NextGen IT tracks this cost as a fiscal year operational cost. DoD mandates the use of Real Property Information Model, or RIPM, and the operational cost is an element of that model. As shown here, you can open any real property record in NextGen, then click on the Operational Cost tab to see a fiscal year summary of all work task costs. Not every CE customer on an installation is covered by CE funding and therefore must reimburse CE for maintenance services delivered. We will cover reimbursable billing in greater detail in just a moment. The ops flight needs to pay particular attention to establishing methods to ensure data accuracy. For example, it's easy to make the mistake of entering 11 hours of time when the correct entry was supposed to be 1 hour. Failing to enter GPC costs of materials purchased directly by shops is another typical culprit of data inaccuracy. Selecting the wrong building or customer leads to incorrect work task cost flow to real property and cost accounting business processes. Now that you have situational awareness of work task cost at the macro level, let's dive a little bit deeper and take a look at the details of shop rates, material costs, and reimbursements. Understanding shop rates is an important element of being in the operations flight. The shop rate helps us convert time logged in hours into a dollar value that can be associated as a work task cost. The shop rate is a ratio of the cost of doing the ops flight business divided by the total number of direct hours performed. The numerator has 3 elements. The largest portion is always going to be the personnel costs, which simplistically can be considered salaries of civilians, military, and local nationals. Also included are indirect materials used in the everyday business of performing work. Finally, vehicle costs such as fuel are included in the shop rate. As more hours are logged during work in relation to the costs, the overall shop rate will go down. Conversely, if an ops flight logs fewer direct work hours in relation to their costs, the shop rate will go up. Material cost capture requires significant attention to detail. Underreporting true costs impacts both work task total cost value and shop rates. The majority of a work task's material cost comes from consumable items used by technicians to complete the maintenance or repair action. We call this direct material cost. These items are intended specifically for this one work activity and no other. Note that if items are not used or excess quantities exist after the job is done, the return of those materials using proper processes will reduce the direct material cost on the work task. On the other hand, items issued to work groups or people directly in those work groups is considered indirect cost. These items are necessary for the shop to perform work and include items such as safety gear, tools, and spare blades. But none of these are directly connected to the performance of a single specific work task. Instead, as we saw earlier, these costs are included in the overall shop rate. Wrapping up, R&O needs to provide top-cover quality control for material cost. Be on the lookout for unusual indirect material issues and large costs. Only MAC Control can buy and issue indirect material in Next-Gen IT. Finally, analyze material spending per labor hour as a good indicator of shop hoarding or sloppy data entry business processes. This table shows the percentage of cost by work task priority. Labor and cost percentages tend to be very similar since labor is usually the main cost. Preventive maintenance typically has lower material cost, while priority 4 work tends to be higher. Let's conclude our cost discussion with the hot topic of reimbursements. Customers, like lodging, fall outside CE funding support and must pay their own way. Reimbursable customers have a Next-Gen support agreement that defines their reimbursable status. Be aware that the ops flight should always rely on their financial manager as the expert for their local reimbursement program. If a customer must pay for labor, then it makes no difference who actually goes out and does the work because the shop rate defines the labor cost to be reimbursed. Unlike military labor costs, civilian labor costs do come back to the installation. While the cost does not directly come back to the civil engineer squadron, it does indirectly support CE by helping the wing cover an unfunded portion of their total civilian pay bill, which in turn reduces what units must give up to cover the gap. Material cost is directly reimbursed to CE and will likely go to the ops flight. This is why the earlier emphasis on material cost is so important. AFI 32-1001 states the operation flight's main objective is to effectively and efficiently operate, maintain, and repair Air Force real property and real property installed equipment through employment of asset management principles. At this point, it may be unclear what we've covered so far and the AFI statement have to do with strategic maintenance planning. To better understand asset management, let's take a look at an example that you may relate to. You may be surprised to discover that you are in fact unconsciously making strategic decisions over the life cycle of an asset you're probably very familiar with. Most of you have probably purchased a vehicle. Whether it was new or used, in either case, you probably had to come up with either a large amount of cash or the ability to obtain a loan to cover the cost of the vehicle asset. Your expectation was most likely to get beneficial use of that vehicle to provide transportation and activity for a fairly long period of time. Because of the great investment and high expectations, most new vehicle owners tend to enter a honeymoon period with the new asset. The early stages of vehicle ownership tend to keep the vehicle in great shape, clean, and likely the owner takes advantage of any warranty work and all minor preventive maintenance. As time marches on, the honeymoon transitions to basic reliance on your vehicle to meet your transportation activity requirements on a regular basis. Dependence on your vehicle to meet your personal mission needs is predicated on the vehicle asset's ability to perform reliably as expected and whenever needed. The next phase of ownership entails keeping the vehicle running at peak performance with the least amount of resource investment. Thus, an owner may have no decision-making problem or funding constraints about taking their vehicle in for regularly required maintenance and even the occasional corrective maintenance action because the return on this small investment results in continued transportation reliability. Continued use puts wear and tear on the vehicle asset, requiring more complex and costly maintenance to keep the vehicle operating. Now, the cost to you, the operator, in both loss of use and increasing maintenance bills, reduces the return on investment from an ownership perspective to exercise those repairs. In fact, you may be willing to live with the problem and run the vehicle to failure. Some end-of-life decisions may be forced upon you, but hopefully your strategic decisions realize years of reliable transportation under your ownership. Developing and executing a methodical approach to maintenance and repair optimizes your return on total cost of ownership and prepares you for the next cycle. Using our vehicle discussion as a baseline, let's look down across an installation's built infrastructure and map out key points in the strategic maintenance of an asset over the course of its life cycle. At the very beginning of ownership, we should rely to the maximum extent possible, and where it makes sense from a return on investment, on the use of free warranty support from the manufacturer or service provider. Additionally, we should begin following manufacturer maintenance recommendations, especially for preventive maintenance in accordance with AFCEC Operations Maintenance Branch recommendations. Low investments at this stage should have higher rates of return towards maximizing the overall useful life cycle of the asset. As we just saw in the vehicle example, continued use of the asset and the associated wear and tear resulting in degradation will require both unscheduled service as well as recommended scheduled service actions to keep the good condition good. This is often considered the sweet spot of maintenance investment for asset management. By investing proactively, the overall life cycle investment cost should be lower to keep the asset performance satisfactory. While the civil engineer goal is to avoid emergent requirements, they will occur. Here's where strategic decision-making and actual results may conflict. At this point, analysis of the mission requirement and impacts from the degraded state need to be considered for courses of action. Do you repair at all? Do you repair with in-house technicians? Will you be able to secure funding for a contract in a timely manner? Eventually, you will get to a point where continued investment in an asset is a poor resource allocation decision. At this point, your best option is to run systems or components to failure where possible and simultaneously be programming a replacement. This tail end of life can have significant implications for the operations flight, because this is where we can seek to gain shop time by no longer performing as much preventive maintenance, or any at all, as well as reducing our level of support to the asset in general. Just like you as a vehicle owner might have accepted risk toward the end of life of your vehicle, our mission partners may accept reduced functionality of their facilities and assets as replacement options are pursued, because no mission capability is far worse than having somewhat degraded mission capability. As an asset ages over time, you will be evaluating a continuum of risk tolerance both from the perspectives of mission execution as well as the infrastructure performance and maintenance cost. The majority of the asset's useful and productive life will encompass what we consider from an operations flight perspective the need for a strategic maintenance plan that outlines recurring levels of support, when to proactively invest in requirements, and when to ignore requirements with the goal of optimizing performance at the lowest cost. Finally, understand that the total cost of ownership spans the entire spectrum of the asset's life, from its earliest infancy and design all the way through demolition or removal. Strategic maintenance planning relies on the ability to balance necessary responses to reactive requirements, but infusing strategic proactive requirements as well. The R&O Balancing Act for maintenance scheduling relies on the ability to migrate from a reactive, essentially unmanaged scheduling process to become more proactive and optimized. Schedule effectiveness measures doing what you plan to do, when you plan to do it, and for how long you expected it to take. The goal is schedule predictability and hence reliability. The journey to strategic maintenance planning begins with a solid understanding of where your requirements come from. This column represents the percentage of log time we saw earlier in a table format. While we cannot predict all emergencies, history does provide us a good benchmark, and for certain shops is in fact a very good indicator of seasonal workload. So budgeting some of our schedule capacity to cover these emergent requirements makes sense. Both preventive maintenance and plant operations provide us great schedule reliability because we know in advance the capacity of work for a given schedule period. These two categories should be the easiest to schedule time for. As a single discrete requirement, priority 2B work should easily be forecasted and overall will take very little of our total schedule time capacity. Enhancement work can indeed be a direct mission support requirement. However, in most cases, priority 4 work is not reactive and has schedule flexibility to accomplish with specific mission need dates. You may recall we saw earlier that corrective maintenance work consumes about 2/3 of our total logged time. So the key to implementing an optimized strategic maintenance plan is really understanding where your corrective maintenance requirements actually come from. If you operate with a mostly ad hoc, highly reactive, very external customer influenced scheduling process, and I use the word process loosely, then your program will be highly reactive and have a very poor schedule reliability. Additionally, you will likely be missing out on critical opportunities to perform sweet spot maintenance investments based on recommendations from our sustainment management systems or technician discoveries during maintenance visits. But if we could flip this around and turn the source of our maintenance requirements to favor proactive management efforts by portfolio managers, as well as giving priority emphasis to technician inputs, we might discover we can actually reduce the overall percentage of requirements reactively coming from customer service requests. Just setting a goal of reducing corrective maintenance requirements from external customers by 25% sets you on a path for success. But let's be clear. This effort requires perseverance and leadership support. Additionally, optimization efforts take time, in part to learn from your mistakes. Don't worry about early setbacks and focus on the end goal. We've placed emphasis on the establishment of proactive maintenance requirement sourcing in order to improve predictability of maintenance requirements, feeding a strategic maintenance schedule. And we've seen that lifecycle ownership involves making the right maintenance decisions at the right time to maximize operational longevity at the overall lowest cost. To achieve effective maintenance scheduling, you must look hard at your current capacity to perform work. How many hours do you have to spread across all of your maintenance requirements? Used correctly, this information can be a powerful ally. Your customer's perception of CE is as a big squadron with unlimited capability, and your manning document and large parking lot reinforce that belief. Ops flights tend to have a poor understanding of their own capacity to do work and thus cannot explain it to customers. If you understand and apply these 4 scheduling laws, then you'll be well on your way to success. First, you only have a finite number of hours at your disposal. The number of people assigned times the hours in a day sets this finite limit. Overtime can extend normal duty hours, but only goes so far. The next rule states that some of those hours will never be available for work, but instead are consumed by indirect hours managing a shop, like supervision, or hours lost to leave or training necessary to overall personnel management. Thirdly, in any given time frame, we do know with a fair degree of accuracy how many hours will be required for some maintenance activities like preventive maintenance or plant operations. From a scheduling perspective, we will remove these hours off the top of the total hours we have for executing maintenance. The 4th law states that corrective maintenance requirements vary widely in the length of time to complete, whether scheduled or unscheduled, and thus will require the greatest oversight and discretion in managing to optimize scheduling capacity in order to accomplish the right work at the right time and still support strategic life cycle goals. Effective scheduling seeks to remove variation or unpredictability as much as possible and relies on predictable information as much as possible. This is why any schedule insert from a bona fide emergency to a special interest do-it-now project can create havoc with a poorly managed schedule. Your goal is to apply scheduling concepts like booking maintenance and budgeting for likely contingencies to accommodate predicted variations that leaves the overall schedule on track. Booking maintenance describes the assignment of labor hours available against requirements. The requirements being booked or earmarked for accomplishment may in fact be a combination of both unknown but expected work, for example, known historical trends or emergency workloads, and for very specific work, such as a builder recommendation work item to replace a system component. However, to be able to start reserving this time, one must first establish what in fact is the size of your maintenance paint can. Thus, it would not be prudent to begin committing to workload when in fact you're not even sure how much time your shops will have to perform the work in the first place. The process starts with converting staffing to a total number of accountable hours for the schedule period. This result is then decremented by various factors such as your indirect time for supervision, training, etc. Additionally, requirements such as emergency work and PM will be considered must-dos and can also be budgeted for up front. The rest of the time to be scheduled for the shop will be considered on a discretionary management basis and applies a mix of mostly corrective maintenance workload and perhaps some enhancement work. The goal of this process is to ensure a firm understanding of the likely number of hours at the shop's disposal and then only feed shop requirements up to but not exceeding its capacity. This is a bit like the old airline passenger overbooking issue where 150 seats can only hold 150 passengers, not a single one more. Instead of booking seats, you are now booking available maintenance hours within your discretionary schedule capacity. Okay, let's walk through a simple exercise. Let's assume we have a shop with 17 folks, including the foreman. Let's also assume our planning period is for 1 month. In this month, we have one federal holiday, so if you count the workdays, we only have 21 total. Let's also make this easy and assume an 8-hour workday. Doing some quick math gets us to just shy of 3,000 hours for the month, which sounds pretty good. Or is it? Hey, what in the world has happened to our shop? The hard reality is we never get the maximum hours per person for a planning period, regardless of military, civilian, or contractor. We lose hours from a host of reasons as shown here. These absences reduce the available hours we deploy to actually perform maintenance on the installation. Often, ops leadership focuses exclusively on the total unavailable hours. What should also be examined, however, is the scheduling efficiency of those hours. For example, it might be better to have an essentially down afternoon for all training versus constant training absences throughout the schedule. So it should be pretty clear our 17-person shop is not going to generate 2,856 hours of work. Assigning monthly workload to this shop for anything even close to that number of hours makes no sense. Doing so will immediately start a backlog of unfulfilled requirements. The availability rate is the ratio of direct usable hours over the total number of usable and unusable hours. Let's walk through the process to determine how many hours might really be available to work. Obviously, you'll need to know how many people are assigned. Additionally, you'll need to calculate your availability rate. You can do this by running reports in NextGen IT to determine how many direct hours and indirect hours the shop logs on average. Seasonal information can be found by looking at last year's information for the same month. Then we need to make some basic assumptions. Here we're going to assume an 8-hour workday, and we'll use that same 1 month with 21 workdays, and still no overtime. The contingency reserve rate, or CRR, allows us to book slightly less than our theoretical maximum number of hours, and in this case we'll use a 10% value. This action sets a planning buffer to allow for unexpected requirements or work that exceeds the estimated time to complete without busting the schedule. The Schedule Period Capacity, or SPC, uses the formula shown and determines your total capacity in labor hours to do maintenance for the schedule period chosen. Responding to emergencies, accomplishing preventive maintenance, or plant operations is considered non-discretionary work because you just have to do it. For Priority 1 emergencies and Priority 2A plant ops, you can look at your history to get a sense of the hours you'll need for this planning period. If you have a mature preventive maintenance program in NextGen IT, you should be able to look at the total number of scheduled hours for the period of time in question. The non-discretionary schedule rate, or NDSR, is simply the sum of the percentages of Priority 1 work and Priority 2A work you plan to allocate. Since the discretionary schedule capacity, or DSC, reflects the total number of hours available after removing the non-discretionary commitments, you can use the formula shown here to calculate its value. The DSC then becomes the limiting factor in your overall maintenance schedule and restricts what you can expect the shop to complete. The DSC requires the greatest amount of management attention towards optimizing an effective schedule. Okay, admittedly that was a lot of information to absorb all at once. So let's go a little bit more slowly with some actual numbers for our imaginary shop. Our shop has 17 people assigned. And based on some analysis, we've discovered our availability rate, or AR, is 61%. It should be noted that sample is using a percent based on the average availability rate for our shop. However, if you know the actual non-available time for the month, you should use that total number of hours instead. You would remove AR from the equation, do the math to get the total number of schedule period hours, and then subtract from that value. We will continue to schedule for the period of 1 month, and let's keep the contingency reserve rate of 10% to cover any unexpected pop-ups in our schedule. So to calculate the schedule period capacity, or SPC, for this month, we take 17 people times the AR rate of 0.61 times an assumed 8 hours per workday times 21 workdays in the month times our adjustment for contingency reserve. That comes to 1,568 hours for 1 month that we can schedule. So unless we end up approving overtime, this is the maximum number of hours we can expect this shop to log during the month. Our shop history suggests we've spent 2% of our time responding to emergencies. Additionally, this shop spends 25% of its time performing mostly preventive maintenance and a very little bit of plant operations. So in this example, we are budgeting 2% plus 25% for a total of 27% of our time as non-discretionary schedule requirements. To calculate how many discretionary hours we will have in this monthly schedule, we take the SPC value of 1,568 hours and we multiply it times the percentage of time left over after removing our non-discretionary budget, in this case 100 minus 27%, to arrive at the value of 1,145 hours of discretionary schedule capacity, or DSC. Remember, the sample is using percentages, but if you know the actual number of hours you will need for both preventive maintenance and plant operations, you would use those raw numbers and subtract from the SPC to be able to determine what your discretionary schedule capacity will be. The DSC is all the schedule hours you can safely book, but we are still holding 10% of our SPC in reserve just in case. If you want to get a feel for how many hours per day the shop can be scheduled to accomplish all Priority 3 work and all Priority 4 work, then you can calculate the effective daily capacity, or EDC, by taking the discretionary schedule capacity and divide by the number of days in your schedule. Running that calculation for this shop, we can take the 1,145 DSC hours divided by the 21 days in a month to discover this 17-person shop can really only be scheduled for 54.5 hours per day. That's slightly less than 7 full-time employees that will have to cover all of your other maintenance requirements. Calculating the SPC and the EDC provides both you and the shop awareness of the practical booking limits scheduling work for the time frame selected. Let's briefly cover 2 other aspects of scheduling. First, understand there are a variety of scheduling evaluation factors that have to be considered. In addition to urgency, defined both by maintenance urgency as well as the impact of the mission, civil engineer executability is critical. For example, you simply cannot work on a roof in the middle of a lightning storm. Note that customer focus is actually the third listed, and that's done intentionally because the first 2 should receive higher weighting in your decision making. FIFO is not necessarily a good method when considering travel time to job sites and accessibility to some of those locations. You can gain scheduling efficiency by bundling work in same or similar work areas. Another aspect of scheduling is the amount of R&O direct work requirement throughput to shops for schedule execution. Taking the risk of dealing all work directly to shops is simply easier to do because it avoids the effort of determining if the work is being done at the right cost and at the right time. strategic lifecycle management decisions will be lost. This action feels like being more customer-oriented, but in the long term it will not be. However, a percentage of requests should go directly to shops with limited analysis because shops should be able to make resourcing decisions on small-scale requirements more quickly. Passing all work requirements to R&O for in-depth analysis may be another extreme to avoid because that process may have unintended consequences of holding on to work that really didn't need strategic decision-making and delayed response to customers. Holding work for portfolio execution evaluation may feel less customer-oriented, but in the long term you're doing them a benefit. Finding the right balance is the key to overall strategic lifecycle asset maintenance planning. There is one more measure that must be taken before we can apply what we've been learning to practical scheduling process. In order to book maintenance, you must be able to take each work task received and assign an estimated amount of time for completion. Ideally, every Priority 3 work task should be assigned a planned number of hours. The good news is, you don't have to provide an engineering estimate, but more a simple shop estimate based on experience with similar work requests or perhaps having worked in the same facility before. The assignment planning estimates can be split between R&O for the larger work and allow the shop foreman to tackle the smaller jobs. Next-Gen IT allows entry of the planned number of hours directly on the work task record. This action, in turn, allows one to run reports and use tools like Excel to manage the total number of hours to be booked for the scheduled period. Then, over time, R&O in the shop can analyze planning estimates versus actuals to refine the process and allow the assignment of estimated hours to become more accurate. One other note. While this may sound like a daunting effort, initiating the process to even cover just a subset of the total shop schedule, for example, only provide estimates for larger expected jobs and simply block a number of hours for small jobs, will gain overall efficiencies. Furthermore, this rigorous process establishes the ability to effectively measure schedule compliance by comparing not only what you plan to do in the maintenance schedule period, but also taking a look at how closely you stayed within your non-discretionary and discretionary budget allocations. Also examine how close was your contingency reserve rate in covering growth within the planning period. Many operations flights simply count the number of work tasks received and look at the shop's completion versus assigned rates. This is overall not an effective measure of schedule compliance. Let's go back and visit with our foreman and see how he's going to manage his shop scheduling for a 17-person team. He's created a schedule planning board for 1 month. On the left side, we can see he's written down his schedule period capacity hours of 1,568 that we calculated earlier, and he's divided by 4 weeks to discover he has about 392 hours per week. He's also recorded his non-discretionary workload in both percentages and hours. Finally, he subtracted those hours to calculate his non-discretionary capacity as 1,145 hours, or on average about 55 hours per day. Looking across the top of his board, we can see he's divided it for each week of the month. Because he's the foreman and knows more details about his team member availability, he was able to actually determine the total number of schedulable hours for each week versus using percentage averages. Adding each week's SPC will total up to the monthly value of 1,568 hours. Next, our foreman began managing the schedule time for non-discretionary work. First, he looked at emergency history and determined about 2% of the time needs to be reserved to cover emergent unplanned requirements. He multiplied his total SPC times 2% and divided by 4 weeks. He found he needed to budget 7.84 hours, which he rounded to 8, for each week. Next, he took a look at his planned Priority 2A work and recorded the actual hours for each week as shown here. Note that in the second week, because the total SPC was lower, he reduced the schedule budget for Priority 2A work. On the next row in his schedule planning display board, he calculated the DSC for each week. So in the first week, he took 436 hours, subtracted the 8 hours for Priority 1 work, and the 125 hours for his Priority 2A work, resulting in 303 hours. He repeated this for every one of the remaining weeks. Adding up each week's DSC brings us very close, 1,144 hours due to some rounding errors, to the NDSC shown on the left side. Next, we see our foreman booked or assigned work up to 90% of his available time to schedule for discretionary work. Furthermore, he divided work smartly into zones of the base to help minimize overall travel time. For the remaining weeks, notice how our foreman's booking rate decreases with each week. Why is this? From the foreman's perspective, he really knows what's going to happen the next week. However, each future week brings a degree of uncertainty, and therefore, he's only going to book a smaller percentage of discretionary work because he does not know what else may be coming in, nor does he know if the first week's jobs will meet their planned completion times. As new work arrives during the month and then gets assigned to the shop, our foreman begins allocating schedule time for those new requirements against the future weeks. Around the middle of the week, he evaluates where the shop's overall schedule compliancy is in order to make any adjustments before the week ends. Then, as the first week is concluded, the second week now moves into the first week slot and is booked up to the 90% rate, and each of the subsequent weeks moves into the new position with a brand new fourth week being added. Because we just learned how important it is to be able to provide some level of planning estimate for each corrective work task received, our foreman is taking advantage of lead technicians to assist in the overall planning process. Lastly, in an attempt to provide further optimization to the schedule, our foreman is looking at dedicating some of the technicians to emergency, preventive maintenance, and corrective maintenance activities for each week in order to minimize their daily disruption and allow consistency in completing the assigned work. He's also trying to reduce surprise non-available pop-ups by requesting his team provide all appointments and schedule requirements a week in advance. Hopefully, you now see value in this methodical scheduling approach. Let's introduce an overall strategy that R&O may use to optimize maintenance activities. We begin by relying on our foreman to manage at the tactical level, keeping up with his weekly goals in the overall scheduling month. His schedule interaction will always be the most dynamic and require constant fine-tuning and hopefully mostly small-scale juggling to stay on track. He needs to be prepared to move work scheduled for the future to be accomplished earlier as a result of changes due to weather conditions, or maybe even getting work done faster than anticipated. The superintendent should be taking a more strategic look over a 3-month quarter for all the shops they oversee. The supers should be working with R&O and taking a look at analysis. For example, is preventive maintenance keeping corrective maintenance at the proper threshold? A primary strategic role should be working with R&O as a bridge to the shops to help ensure sub-manager portfolio goals for in-house work recommended by sustainment management systems gets appropriate schedule priority and leadership focus. Orchestrating the whole maintenance program is R&O, whose sub-ant managers act like generals on the maintenance battlefield, directing strategic engagement of maintenance forces at the right place and at the right time to preserve and prolong the built infrastructure health for the required cost-effective life cycle of each and every asset. We've journeyed far, but our climb is not over. Let's very briefly take a look at the vantage point analytical tools like sustainment management systems such as Builder, or data visualization tools such as the Next-Gen IT Work History Dashboard can provide to our strategic maintenance plan. These tools provide a commanding view of asset health and can shed light on conditions requiring maintenance attention. Maintenance forecasting is no longer a needle in the haystack drill. Today, your problem will be sifting through the many choices presented to determine the optimal use of in-house versus contract execution methods. Make sustainment management systems like Builder your best friend. Be sure to learn how to use the tool to develop lists of asset maintenance recommendations. Remember, Builder's thinking about every asset today and where it will be in the future. While SMS tools model predicted asset degradation, your Next-Gen IT Work History captures actual maintenance trends over time. This easy-to-use tool is managed by AvCAC on your behalf. Once you acquire a Tableau Viewer license, simply log into the tool to be able to filter data for your local analysis. Data for all Next-Gen completed and closed work tasks, beginning with fiscal year 2018, are included. You can easily filter to a date range you need. Clicking on a building in the Work Task Summary table filters the data and additionally brings up the building system scores if available. The trend graph at the bottom can be viewed by 3 different values for work task count, hours, or total cost. A portfolio manager might be interested in further filtering by 1 or more shops to get a sense of maintenance history for that class of systems. Clicking on any table column header allows you to resort the column to find the largest values quickly. It's easy to filter all the data to a single facility, customer, category code, or other filter choices shown on the left. Once you have all the necessary filters, you can select on a line in the responsible organization summary to reveal a link to view all the individual work tasks generating the view. The dashboard also lets you quickly view all emergency work trends to determine if you have a systemic asset health and maintenance issue. Be sure to check out the AFTEC Operations Maintenance Business Process Library, or BPL, for additional in-depth discussion on requirements data analysis. Take advantage of AFIT and AFCEC offerings to broaden your skills to apply hard analysis of data to inform your decision making. Deferring requirements is going to be a legitimate action taken by the R&O team. Let's briefly discuss why we may end up needing to defer a requirement, but we'll start with reasons to not accept work at all. First, we may be able to eliminate some requests simply because the nature of the work is not CE's responsibility in the first place. This is the easiest reason to say no. Next, a requirement may come in that does not make sense in the long run because of other actions planned for that facility. As we saw at the car ownership example, living with degraded condition and sometimes running to failure is a good course of action. The most likely scenario is that the maintenance request, whether from a customer or internally generated based on analysis, will simply be too small for programming as an opportunity, but at the same time exceeds the capacity of the ops flight to schedule in their planning timeframe. Executing by customer-funded contracts may be an appropriate course of action, but recognize this will take additional civil engineer oversight to manage properly. In some cases, you may be able to defer the requirement back to the external customer by letting them manage on a unit priority list of their requirements. This action may allow CE to gain additional time until the overall conditions improve to accept the requirement. Do you remember the first law of scheduling? Oh, that's right. We only have a finite number of hours to schedule. Therefore, the practice of accepting any and all work requirements really makes no sense because you know right up front you won't be able to accomplish them. This logjam of unexecutable work will create administrative headaches for CE as well as cause customer relation issues. Take a hard look at this definition of CE Ops Flight Deferred Maintenance. Your goal should be to never allow your schedule planning to exceed the practical horizon of what you really can execute. Therefore, a 6 to 12 month range is typically the optimal time window to consider for planning purposes. Accepting customer requirements that support sub-manager portfolio goals and can be reasonably expected to be done by in-house shop execution can be added to the strategic maintenance plan. However, priority should be given to SMS-generated requirements when they meet sweet spot investment goals. Grouping requirements may ultimately lead to execution by alternative means. Okay, if you've accepted a customer's requirement as being legitimate and it fits within lifecycle planning goals, make sure to engage the customer with appropriate expectation management. If you engage them with condition assessment analysis, work history, and CE resourcing restrictions, you may be surprised at how well you can partner with them on the requirement. Preventing smaller requirements from falling through the cracks is a critical R&O management skill. As just mentioned, accepting all work, which does allow customers to throw the problem into your backyard, is a bad management practice. Accepting legitimate requirements and deferring them for an optimal execution timeframe and method is absolutely a good process to establish. However, recognize that deferred requirement management requires rigorous attention and review to ensure the requirements remain valid, and you must pay attention to execution windows of opportunity. Fortunately, NextGen IT provides a management capability to track those deferred requirements. use the work task's tracking status field and select the hold for optimization value. Most work management community reports have a filterable column for the tracking status, or you can write your own report. One more very critical tip. Before you defer the work task, be sure to add a planning cost value or number of hours. This critical action will pay off handsomely in the future when you're looking at your growing list of deferred requirements and trying to make execution decisions. Well, we're coming to the end of this presentation and the beginning of your role in operations flight, maintenance, optimization, and strategic planning. We learned that 2/3 of our time has been logged to Priority 3 work and that corrective maintenance requires discretionary scheduling oversight. Capturing accurate cost data on each work task record is a critical responsibility for the ops flight. We learned about the 3 types of costs being recorded and the importance to other business processes for civil engineering. Next, we took a look at the total cost of ownership using an example of a vehicle and applying the various phases of strategic maintenance planning to an approach for built infrastructure lifecycle management. Understanding a shop's true capacity to perform work is foundational to the ability to effectively schedule work. We followed a foreman and his analysis of his schedule period capacity for work and the major sub-elements of non-discretionary and discretionary booking. We also examined a shop scheduling concept in greater detail and emphasized balance between the shop and R&O requirements management. We then explored how strategic maintenance planning, from R&O to superintendents to the shop foreman, can effectively ensure that critical sweet spot maintenance investments are executed at the right time. A variety of analytical tools exist to assist in this overall process. Lastly, we reviewed the definition of ops flight deferred work, considerations for accepting work to be deferred to an optimal execution time and/or method, and next-gen capabilities to manage those deferred requirements. Your mission partners are an amazing group of folks who perform an astonishing array of missions, and they're counting on you to be equally amazing in your ability to provide and care for built infrastructure for the long haul so they can achieve success in what they do.